Welcome to your third lesson for Unit 6. We are still talking about circular motion. We're going to kind of transition into a different topic now. There's a lot that goes into this one unit, and it's all related, but because you can apply circular motion to so many different parts of life, it does kind of feel like we're going to jump from thing to thing to thing. Okay, today we're talking specifically about Newton's law of universal gravitation. Please let yourself be amazed by this. We'll continue chatting about this as we go through this lesson. It's really, really cool that this law holds true for so many things. So let's get into it. All right, so Newton, honestly, what a dude. He did so much for physics, for gravity, for just the human race in general. What a guy. So Sir Isaac Newton articulated his 3 laws of motion. You already know these, okay? So this is a little bit of review. Hopefully you're saying them, you're thinking them. Number 1, an object in motion or at rest stays in motion or at rest unless acted on by some kind of force, unless a net force acts on it. Okay, that's number 1. Number 2, what's number 2? FMA, F equals MA. Number 3, hopefully you're saying this one too, for every action, there is an equal and opposite reaction. All right, so you know these. This is just a little bit of review. This usually is what we think of when we think of Newton. We think of Newton's 3 laws. But Newton did a lot of other stuff too. He also worked on planetary motion. So, I mean, if you think about his time period, he didn't have all the tools and calculators and computers that we have today. And he still was able to formulate some pretty amazing laws that we still use today that no one has disproved yet. They hold true. So he especially focused on how the moon kept its orbit around the Earth. So we're going to have a bunch of problems today where you're going to be dealing with things in space. You're going to have some really large numbers that you're working with, lots of scientific notation, okay? So just to prepare you, Newton observed that, Newton observed that objects accelerate towards the Earth no matter their location or height. So we've talked about this, right? It's the force due to gravity, right? If a force is exerted on an object, it must be exerted by an object. In this case, the Earth exerts a gravitational force on objects near its surface. But what Newton wanted to kind of do with this is he noticed that, right? And maybe you've heard the story about how like an apple fell on Newton's head and he was like, oh, gravity. Like he wanted to see, could you expand this idea? Could you take it to space? Could you apply this gravitational force concept to orbits and to other planets that we know are in orbit around other objects? So that's kind of where we're going with this today. Newton set out to prove this. So not last week, but on Tuesday, we actually calculated the centripetal acceleration of the moon. And we said that it was 0.00272 meters per second squared. When we compare this to gravitational acceleration on the Earth's surface, so what I mean by that gravitational acceleration, I mean g. Usually we use 10 meters per second squared. More officially, it's 9.8 meters per second squared. So when we compare those two numbers, 0.00272 meters per second squared over 9.8 meters per second squared, or you're comparing it to g, Newton found that this relationship, 1 over 3,600 times whatever that accepted value of g, gravity, is, this is what it kind of simplifies to, okay? And this is an interesting result because the moon is 384,000 kilometers from the Earth, and that's about 60 times Earth's radius. So this is interesting because there is a clear link between 60 and 3,600. 60 squared is 3,600. So what Newton did was he recognized this relationship And he said, okay, so the force between two centers of attracting bodies, so, bodies we know can mean anything like an object, in this case the moon and the earth, the force decreases as the square of the distances between those two centers increases, or stated as a proportionality statement, F, which you can think about here as the force of gravity, is proportional to 1 over r squared, and r would be that distance between them. So similar to the r we've been using in other circular motion, right? That r we were saying was from the center of my circle to an object in this circular path. Here r is the distance between two objects, the centers of two objects. So if the moon is 60 times the Earth's radius away, then the force of gravity would be 1 over 60 squared, or 1 over 3,600. So that's where he was getting that relationship from. Newton went further to recognize that force also depends on mass. So now he's saying force is proportional to the mass of the Earth and the mass of whatever object we're dealing with. He was talking about the moon, could be any object, over r squared. So you need to take both masses, the mass of the Earth and the mass of the object, into account. Take both masses into account here. All right, he kept going with this, and he came up with his law of universal gravitation. And this law, please take a second, let this soak in. Every particle in the universe attracts every other particle with a force proportional to the product of their masses and inversely proportional to the distance between them. This force acts along the line joining the two particles. So our equation here is F, this gravitational force, equals G. G is just a new constant. I do not need you to memorize this. I will give you this constant on quizzes and tests. It's a constant the same way like pi is a constant, right? So he found out for any relationship between any two objects, you're going to have a bunch of constants in there. And so we just kind of simplified them into G, which represents this large number, 6.67 times 10 to the negative 11th. I guess that's actually a very small number. This very small number. Okay, back to the equation. F, this force, G, mass of object 1 times mass of object 2 over the distance between the two objects. So R is the distance between the objects. This is mass of object 1. This is the mass of object 2. G is your constant. And seriously, pause here. Well, don't pause. Keep on listening to me. Every particle in the universe attracts every other particle with a force that follows this law. Is that not so cool and amazing? Every particle. So we're talking planets. Every planet attracts every other planet with a force that follows this law. That's so cool. Every single particle. We're talking on the atomic level. You're talking about tiny little atoms. We're talking about people. Every person in the universe attracts every other particle in the universe. Like, I count as an object. So, yikes. I don't like that. A person we can approximate as an object. And you're going to attract another object with a force that follows this law. So you're talking on the micro level. You're talking on the macro level. You're talking things you can see, things you can't see. They all follow this law. That is so cool. And to me, this is just more evidence, more proof of intelligent design. How could we have so many different types of objects work with the same kind of force, if not for some kind of creator God who said, hey, this design works and it works really well. I'm going to have it work for every particle in the universe. Like tell me that is not cool. That is so amazing. Okay, let's apply this. Let's do some examples with this. This first one, okay, you can make some jokes about this. You could come up with a pickup line. If this works, and if I can approximate humans as the different masses and the different objects here, then officially, two people have personal attraction to each other, gravitational attraction. So do with that what you will. Let's do some math. Okay, so mass 1, I have a 50 kilogram person. Mass 2, I have a 75 kilogram person. Honestly, classwork point to the person who comes up with the best pickup line based on this problem here. R, that's the distance between them. They're sitting a nice healthy distance apart. That's good for them, 0.5 meters. And we're going to estimate the magnitude of gravitational force each exerts on the other. So we're going to use that new equation, F equals G m1 times m2 divided by r squared. G is that 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared. So at this point, just go ahead and plug everything in. 6.67 times 10 to the negative 11th. Mass 1 is 50 kilograms. Mass 2 is 75 kilograms. All over 0.5 meters squared. And you'll see that your units are going to work out nicely here, right? Kilogram, that's going to cancel with kilogram squared. Down here, you're going to have meter squared. That cancels with meter squared. You're left with lovely newtons, okay? Simplify, let's say we're going to go to 1 decimal place here using scientific notation. So I'm going to have 1.0 times 10 to the negative 6 newtons. So this is the gravitational force each person in this scenario exerts on the other. It is tiny, but it's still there. It still counts, okay? Once again, even little atoms, tiny little particles will be attracting forces. Eventually, when we get into our electricity unit, we're going to see a pretty similar thing happening at the atomic level. It is really cool. Please let yourself think that this is really, really cool. Once again, whoever comes up with the best joke about this, classwork point. Okay, example 2. We could take this to a larger macro level. So now I'm going to think about a spacecraft. So what is the force of gravity acting on a 2,000 kilogram spacecraft when it orbits 2 Earth radii from the Earth center? So your R would be from Earth center to this spacecraft. They're telling us it's 2 Earth's radii. I would not need you to know the radius of the Earth. These are values that I will give to you. If I don't give you the values you need for homework, if I missed 1 or 2, feel free to just Google them, look it up. If you need like the mass of a planet or the radius of something, you also have a table in the very like front cover of your physics textbook, so you can use that too. There's another table in this chapter in your physics textbook, but I'm going to do my best to give you these values. I will 100% give them to you on something like a quiz or a test. You don't need to memorize these numbers. So 2 times 6,380 kilometers, that's going to be your R value, and you could simplify that a little bit. I'm not going to, because just hang with me for a second. There might be an easier way for us to tackle this problem. G, maybe we need to use G, right? If I'm going to use our new law of universal gravitational equation, that's our constant right there. So you could totally use this equation here. Or instead of plugging in these gigantic numbers, let's just use proportionality. So remember, this F, it basically represents the force due to gravity, okay? On the surface of the Earth, I know the force due to gravity. That would just be the weight of an object. That would just be mass times G, and G we take to be 10 meters per second squared. I know that this force is proportional to 1 over the distance between those two objects squared. In this case, they're saying, well, my distance is 2 times the Earth's radius. Normally, this R value is just the Earth's radius, right? If I'm at the surface of the Earth, then the distance between me and the center of the Earth would just be the Earth's radius. Here they're saying I have a space station, and R is actually 2 times RE, okay? But all that's happened here is my R value that I'm used to for calculating weight of an object, that R value has doubled. If R increases by a factor of 2, how would your force change? Think about it as just plugging in a 2 down here. 1 over 2 squared, well, that would give me 1 1/4. So your new force due to gravity would be 1/4 the weight of this object on the Earth. So F, and sometimes, I haven't thrown this in here, but sometimes you will see a little G, like force due to gravity, gravitational force. It's going to be 1/4 this object's weight on the surface of the Earth. So 1/4 times mg. We know the mass is 2,000 kilograms, and then g we take to be 10 meters per second squared. Plug all that in, you'll end up with 5,000 newtons. So the force of gravity acting on the spacecraft to Earth's radii away would be 5,000 newtons. Okay, so once again, you can use either method here. You can take all of these things and you can plug them into our new equation, or sometimes using proportionality is super helpful. And there is a large chance that I will ask you some proportionality questions on a quiz or a test. I want you to be able to explain how proportionality works for some of these. Okay, so that's where we'll get eventually. Okay, here's a slightly longer problem. You have a lot of really big numbers, a lot of scientific notation here. Okay, so find the net force on the moon. So here's the moon. Due to the gravitational attraction of both the Earth, here's the Earth over here. This is not drawn to scale. And the sun. Here's the sun over here. Huge. So the Earth is going to exert a force on the moon. I'll call it force on the moon by the Earth. The sun is going to exert a force on the moon. I'll call it force on the moon by the sun. And we are trying to figure out what is that net force going to be. And I want to find this little degree over there. So based on this diagram, that's how you're going to figure out your theta value. Okay, so what are our givens? I know the mass of the moon. I know the mass of the Earth. These are things that I would always give to you. I don't need you to memorize them. I know the mass of the sun. And then I have some R values here. So the R between the moon and the Earth, they're saying is 3.84 times 10 to the 8th meters. And the distance between the moon and the sun is 1.5 times 10 to the 11th meters. So what we need to do here is we need to calculate these two forces, the force on the moon by the Earth, and you're going to be using G m1 m2 over r squared. M1 would be the mass of the moon, M2 would be mass of the Earth. Your R would be this one, right? The distance between the moon and the Earth. Okay, so plug everything in. I have 6.67 times 10 to the negative 11th. That's our new constant, right? Newton meter squared over kilogram squared. We have the mass of the moon. We have the mass of the Earth. And that's going to be all over the distance between those two. So 3.84 times 10 to the 8th meters squared. This is an easy thing to forget. It has to be radius squared. Don't leave that out. Please, please, please. When you plug all of these numbers in, and honestly, take a second to actively actually do this. I don't want you to make a stupid calculator error on like a quiz or a test. Make sure you know how to plug these all in. Make sure you're getting the same answer that we should get here, which is 1.99 times 10 to the 20th newtons. Okay, so this is the force that the Earth exerts on the moon. You're going to follow that same exact process to figure out the force between the sun and the moon. So I'm still going to have that G constant, 6.67 times 10 to the negative 11th. I'm going to drop units for this one. Don't hate me. Mass of the moon, 7.35 times 10 to the 22. Mass of the sun is 1.99 times 10 to the 30th, divided by the distance between them, squared. And we're going to get 4.34 times 10 to the 20th newtons. Okay, so those are your two forces. If I'm trying to figure out my net force, there's a little bit of review for us. How do you find net force? If you have two force components and you want the net one, we're going to use Pythag. So it's going to be FME squared plus FMS squared. Plug in your gigantic numbers over here, 1.99 times 10 to the 20th squared plus 4.34 times 10 to the 20th squared. You're going to get a net force of 4.77 times 10 to the 20th newtons. That's your net force. And then based on our diagram over here, I'm going to use inverse tangent of FME over FMS, just once again, based on that diagram that I gave you. So inverse tangent of 1.99 times 10 to the 20th over 4.34 times 10 to the 20th. Because they're both 10 to the 20th, officially you could just drop those. Those would cancel out. 1.99 over 4.34. You can plug it into your calculator either way, and you should get about 24.6 degrees, or you could say 25 degrees. Okay? So that's how you could kind of combine all of this stuff together. This is new info about forces. Now you have more tools in your toolbox to figure out the gravitational forces between objects. But then this stuff down here, that's review. That's old hat now at this point. Do you remember when this stuff was like crazy and new, and now you're just doing that? That's really cool. You've made a lot of progress. Proud of you. I'm going to split this up into 2 videos, so I think I'm going to pause there for this one. In the next one, we'll talk a little bit about geophysics.